Hi, I'm Claire Parkinson, a scientist at NASA's Goddard Space Flight Center, and this is the second of 3 videos, and I'm going to be showing you from where we ended with the first video, which was a set of plots of the Arctic sea ice monthly averages through this long-term record that we have from November of 1978 to December of 2012. And a similar plot for the Antarctic. And in this video, I'm going to show you how we as scientists take these results and come up with something more single-mindedly looking at the trend in the data here. Now, when you look at this plot, because the seasonal cycle is so strong, so much more ice in the winter than in the summer, that's kind of what comes out in a plot when you see the monthly averages. That's the big thing that comes out. Way more ice in the winter than in the summer. However, we really are also interested, in addition to the seasonal cycle, we're interested in how has it been changing over time. And so we want to remove the seasonal cycle. And we use 2 ways to remove the seasonal cycle. There are other ways that you could use, but we use 2. And in this video, I'm going to show you one, and in the third video, I'll show you another. So in this video, I'm going to show you the simplest way of removing the seasonal cycle, which is, instead of looking at the monthly averages, average for the entire year. So all you've got is one value for the year, so you've got the yearly averages instead of the monthlies. So we do this, and since the first full year we have starts with January of 1979, we actually, for these yearly averages, we don't use our first 2 data points, November and December of 1978. So we average for the year, and we actually, when we do the averaging, we actually average the daily values instead of the monthly values, but it's going to be close to the same thing. The difference comes because some months are longer than others, and so therefore we use the daily values to get the real yearly average. So when we do that, for this first year, 1979, we get a value of 12.26 million square kilometers. So we take that data point, and for the 1979 point, we stick that on 12.26 million square kilometers right there. Then we proceed to the next year, 1980. We do the same thing. We average the points. Now, 1980 happened to be a leap year, so there are 366 daily values instead. But we average them all, and we get 12.28, so just very slightly higher. And then we plot that for the 1980 point. And then we proceed on, and we take every year, and we plot it. And now, look at how much more clearly the fact that the Arctic sea ice has been decreasing comes across, when instead of having all the confusion of the seasonal cycle in the monthly average plots, now when we have the yearly averages, by removing the seasonal cycle, this downward trend in the Arctic sea ice, which has received a lot of attention over the past several years because of the loss of the sea ice cover, this satellite record is kind of primary in terms of establishing that loss. And so it becomes clear once you remove the seasonal cycle. However, as scientists, even this isn't quite enough for us, because we really want to come up with, like, what's the line that goes through here that will be the best fit to the data. And in order to get a slope, so we can actually come up with a number saying how much the ice cover has decreased over this period. So we take those points, and we'd like to get a line through it, but it's like you could pick lots of different things. Like in this case, in each of these 4 plots, the data are the same. I've got the exact same data points, which were the same data as on the previous picture. And in the first one, I just simply said, well, let's just take from the first point to the last point and draw a line. But if you look at that line, it's clear that line's not really best, because almost all the points end up above it, so it's not the best fit to the data. But then if you try some other lines, I mean, all these other three, I mean, they're different lines and they go through the data, but scientists don't want to say, well, one person will pick that line, another will pick that line, another will pick that line. We want to be able to have a line that everybody's going to agree is the best line. Or at least everybody's going to agree that you can all obtain the same answer. Now, turns out these two gentlemen from way back over 200 years ago, Gauss in the late 1790s when he was still a teenager, Gauss came up with an idea of how to say when something's the best measurement. Now, it wasn't for a line that he was looking at, but it was the best measurement of a point. If you got lots of measurements and they scatter around, how do you pick the best one? And he came up with a method that's called the least squares method. And it essentially says you want to pick the point such that if you take all the measurements you've got, the distance between the point and the measurement, if you square the difference and then you add up the squares of all the differences from all these measurements, then it's the least value. And this guy, Legendre, who is contemporary with Gauss, he came up with the same method, and they both came up with it separately. So they both independently discovered it. I'm sorry that I could not find a good picture of Legendre. This was well before the camera was invented. So I don't have a good picture of him. The only thing that is known to really be a picture supposedly of him is this caricature. So it's kind of goofy looking, but anyway, I wanted to give him the credit of having discovered this method, and he published it first. So Gauss came up with it first, Legendre published it first in the early 1800s, and they both came up with the same method, and at first it was just for measurements, and in fact, Legendre was looking at the orbit of a comet, so definitely not a straight line here. But this method of least squares ended up then becoming used in all sorts of applications. So this mathematical method, and both Gauss and Legendre are mathematicians, this mathematical method is used very, very widely. And so what it means for our data points, and this is the curve, this is the line that comes up fitting best by this method of least squares. And what it means that if you take the distance between the line and the point, and you square that distance, and you add it to the distance between the line and the point, and you go all the way down, this line is the line that's the best fit in terms of getting the lowest value of this least squares added up. Now, the actual equations to establish what that line is, you actually need to have very elementary calculus to do it. And calculus comes after algebra. So the actual method of getting that line, you do need a little bit of calculus in order to get it. However, computer programs now in statistics packages, if you give them your points and you say you want the linear least squares line drawn, the computer package can draw that line for you. So you could get it without actually yet having the ability to derive the equation yourself. So that's the line, and here's the line without the points around it now, because the next thing the scientist wants to do is determine what number can we present to the media or to our fellow scientists or to the general public as to how much the Arctic sea ice has decreased. And so once we get that line, then what we determine from that line is its slope. And the way you calculate the slope of a line is you look at how far it has changed, and in this case it's gone down. So the values have gone down from the beginning of the line, which was at 12.481 million square kilometers. Our measurements aren't that precise, but we use more decimal points to do subtractions and additions in order not to lose precision when we end up in the end. So it's gone down from 12.481 at the beginning of the line to this value here of 10.663 at the end. So if you do that subtraction, it comes out 1.818 million square kilometers is how much it's decreased. It's decreased that amount over a time period of 33 years. So the slope of the line is negative because it's a decrease, and negative 1.818 million square kilometers over the course of 33 years. Go ahead and do the division. Divide 33 into that, and you end up with negative 0.0551 million square kilometers per year. And then, since this is millions, and it just doesn't look so nice when it's like 0.0, so we changed from millions to just plain regular square kilometers, and so we moved the decimal point over 6 places because that's how you change from millions to regular. And so it comes out negative 55,100 square kilometers per year. So that's the slope of the line. And so our final plot here, we've got our points, we've got our linear least squares line, and we've got the result of this value, negative 55,100 square kilometers per year. And so when people call us up and say, how much has the sea ice decreased, we can say with, from our results that the best squares fit here tells us that the yearly averages have decreased by that amount over this period from from the beginning of 1979, because we didn't use those first 2 points in this yearly average, till the end of 2012. So this is a final number that a lot of people tend to be interested in now because of this fact of changes in the Arctic sea ice. So we then do the exact same thing with the Antarctic. We start with our plot of monthly averages, and then to get rid of that seasonal cycle, which is clearly confusing the issues, because if you look at this, you can't really be real sure even whether it's increasing or decreasing over time, because it's not as obvious as the Arctic case. So we take the values for 1979, we average them, again using the daily values to get the average, and we get 11.71 million square kilometers for that first year. So we plot that point, 11.71 right there. Then we move on to the next year, 1980, and this time we get 11.24, and then we plot that value, yearly average, and then we keep doing that, and we have the computer go ahead and plot all the values for each of the years, and now you can see that overall there has been an increase, and that becomes clear once that seasonal cycle, which has somewhat obscured the issue, once that's removed, you can see that overall the Antarctic sea ice has not been doing the same thing as the Arctic has. The Arctic sea ice was decreasing, the Antarctic sea ice has increased. And so that's the increase. Now, once again, we would like to get a line through it, and so we use the same least squares method that, again, was initiated a long time ago by Carl Friedrich Gauss and Adrienne Marie Legendre. And we get the line through it, the least squares line, and then we proceed to calculate the slope. And in this case, it's not a negative, because in this case, the values have gone up over the time period, and they've gone up by a total of 0.527 million square kilometers. It's still over the same period because we're still using the same data sets. So again, we're going to divide by 33 years, and when we do that division, it comes out 0.016 million square kilometers per year. So that, when we convert from million to regular, moving the decimal point over 6 places, we get 16,000 square kilometers per year. And so we use that value, put it on our plot to get our final plot for the Antarctic yearly averages. So we got our data points, we got our linear least squares line, and then we've got the slope of the line, which gives this important single value of how much the yearly averages have changed over the course of the record. And so now we can see the two. The Arctic sea ice has decreased quite a bit, 55,100 square kilometers per year. The Antarctic sea ice has done something very different than the Arctic. It's increased instead of decreased, but not by anywhere near as much as the Arctic has decreased. So it's increased by 16,000 square kilometers per year. So this was one crucial method of how we can remove the seasonal cycle and come up with a number that we can present to people who say to us, who call up NASA and say, how much has the Arctic sea ice been changing? Or how much has the Antarctic sea ice been changing? Now we've got numbers that we can present, and we've got these linear least squares line that any scientist who has ever done curve fitting would know, would be able to get the exact same line. So it's not like we are picking our own line. It's a line that everybody would agree is the linear least squares fit between those points. That's what math enables you to do. It enables you to get a value that other people are going to agree is the right value for what you're doing.